Good morning.
Good morning.
Good morning.
Morning.
Morning. Okay, so good morning, everyone. Uh, I just like to say
Good morning.
good morning. I'm really impressed by what you did on exam two. So that's our first time to take the exam on Canvas online with the format like one question at one time and the time limit. I think most of you did really awesome. So the class average is 60%. What I did is add 20 points to everyone. So our new average is 73.3%. I want to say I'm sorry for some of you really want to retake the exam too, but we cannot do that. I think one reason is because some of you already saw the questions. So uh, so what I did is curve it. So exam three will be also on Canvas. We'll use a similar format as exam two. except the time limit will increase to 100 minutes. We still want to use the format one question at one time. The exam 3 will be on canvas, start at 9 a.m. April 23rd, the Thursday. You probably will have some of those class conflicts. So do some arrangement, make sure you want to take all those 100 minutes. So the last point I want to say is, as usual, do the homework as soon as possible. Because if you get 100% on all the homework, you will get 150 points, which is equivalent as one of the exams. Okay, any question or comments on the class, on the exams?
For the homework, do we have to get 100%, or it's okay if we get like we miss a couple questions on the homework?
You don't have to get 100%. As in terms of if you complete the homework on the day we have the exam, you can have the chance to replace your lowest exam by the final. Yeah, you don't have to get 100%. If you get, for example, let's say 90%, so you will get 150 times 0.9%. So you pretty much get that much. You will get like 135 points on the canvas. Okay, any other questions? Okay, so if no question, we will start on chapter 19. I hope the exam 3 will a little bit easier than exam 2, because exam 2 have those acid-base buffers titrations, kind of very tedious. All right, so chapter 19 is about chemical thermodynamics. Thermodynamics is about the correlation between energies. So chemical thermodynamics will study how the energy influence the chemical reactions. So that's not totally new, because we already studied some of those thermodynamics in chapter 5. So in chapter 5, we studied the first law of thermodynamics. So altogether, there are 4 thermodynamic laws. So first law is the conservation of energy, which means energy cannot be created or not destroyed. So therefore, the total energy of the universe is a constant. Energy can, however, be converted from one form to another form. The form we means maybe kinetic, maybe potential. So you can convert it from potential to kineticus, or vice versa, or can transfer it from a system to a surroundings, or vice versa. So we learn in chapter 5 what is a system and what is a surrounding. A system is something you want to study. Surroundings are everything else beside something you want to study. So in this chapter, we are more concerned with the directions of the energy flow, where the energy will flow from hot object to cold object, or vice versa. So we want to see in which direction the energy flow or the chemical process, chemical reactions will be spontaneous or non-spontaneous. So there are a couple of concepts in that process about spontaneous. So one concept is enthalpy. We studied in chapter 5. The other concept is entropy. So enthalpy is the heat absorbed by a system during a constant pressure process. And we remember enthalpy, we usually use the letter H to standing for enthalpy. It's kind of a heat. Entropy is the measure of the randomness in a system. So in other words, it measures the distribution of the energy. So where are the energy distributed in the system? So both the entropy plays a role in determining whether a process is spontaneous or not. And in this class, as what I said, we will use those variable name or letters to representing these two concepts. So we'll use H for the enthalpy and S for the entropy. Okay, so any physical process, we can classify them as spontaneous or non-spontaneous. Depending on the direction of the energy flow and the distribution of the energy, a process can be spontaneous or non-spontaneous. A spontaneous process proceeds without any outside assistance. Processes that are spontaneous in one direction are non-spontaneous in the reverse direction. Okay, so you can see the example on the right of the screen in the picture. You drop eggs over a harder surface counter, and the egg break. So that process is spontaneous. And reversely, so the broken eggs recover, get back into your hand, is non-spontaneous. So don't confuse spontaneous with fast. There are fast and slow reactions that are spontaneous. So in another word, spontaneity or spontaneous has nothing to do with fast or slow. Fast or slow, as we studied in chapter 14, has something to do with the activation energy, the energy barrier between the starting point and the finish point. So that will control your speed of the process. Don't confuse non-spontaneous with impossible. Energy can be used to make some reactions spontaneous that otherwise will not be spontaneous. So we can use some of those variables control the energy, and therefore it will control the spontaneous. Okay, so some of the common experimental factors affect spontaneous processes. So there are temperature, pressure, and concentrations. So those are examples can affect spontaneity. An example of how temperature affects spontaneity is ice melting or freezing or water freeze. And you can see in this picture on the screen, if you have some of this H2O, and here is ice, and here is the water, then if you keep the pressure constant, you keep this much amount of material we have, we can control the spontaneity by control the temperature as our common sense. If we increase the temperature above 0 degrees Celsius, ice melt. If we cool the temperature to below 0 degrees Celsius, water freeze. And we know in these two processes, heat is involved or energy is involved. So in the melting process, which means go from ice to water, is an endothermical process. Oppositely, when water freezes from liquid to ice, is exothermic. So what that means is endothermic or exothermic is not really directly correlated with the spontaneity. So spontaneous process can be endo or can be exo. Okay, any questions? Okay, so another concept is reversible or irreversible. So this concept about the processes. Reversible process is not really exist in our really daily life. It's a hypothetical process. So in the imaginary reversible process, the system changes so that the system and the surroundings can be returned to the original state by exactly reversing the process. This maximizes work done by a system on the surroundings. Reversible process is an ideal process that does not exist in reality. So then why we define or why we study those kind of process that does not exist in reality? Well, because some of those thermodynamic quantity like the enthalpy H or entropy S, they are state functions, which means they depend on, or their change depend on the initial state and the final state. So in other words, the change, for example, delta S, depend on only the final state, initial state. It does not depend on your process. So therefore, we can hypothetically define those reversible process, then mathematically, those reversible process property can be calculated exactly. So therefore, we can use those imaginary process to calculate those change of the state function, then use it in the other process. Okay, so to make a process reversible, we see the picture on the top of the screen. For example, the heat exchange between system and the surrounding can be imaginarily made reversible by thinking about we have a smaller, very, very small difference temperature between system and the surrounding. We call that delta T. So we make the delta T so infinitesimally small, very small. So the heat exchange between system and the surrounding so slow. So that's why in reality it does not exist. So you can still imagine your delta T is positive or negative. So if your delta T or T plus delta T, which means your system is have a higher temperature, then heat will go out from the system to the surrounding in so much slow rate. It will take forever to finish, so therefore it becomes reversible. And similarly, if the surrounding has a temperature slightly, very slightly higher than the system, then the heat will come from go from the surrounding into the system. Okay. So this kind of a result of those calculus, if you take calculus, you will know there is a so-called infinitely small change delta x. So in this case, we say our delta T is so small, then we can make this process, heat exchange process, reversible. Okay. So another example of reversible or irreversible process is in this gas expansion and compression example. So in this example, we have our gas. Initially, our gas sample is confined or compressed in this right side of this piston. And then we have this movable partition separate the gas and vacuum. So what we can think about is if we take this movable partition away, this barrier away, and the left side is vacuum, and naturally, so when you take this piston away, take this away up, then you see the gas spontaneously expanding to take all the volume of the piston. Okay. So the gas spontaneously fill the evacuated space. And so this process of this gas expanding to take all the space is the irreversible expansion of gas. And how much work is done by the system is zero. So as we learned in chapter 5, there's a work from the expansion and compression of gas. So we remember the formula is W equals negative P times delta V. Okay. So from this formula, we can say W equals 0 because pressure on the left side is 0. Vacuum. Vacuum means pressure equals 0. So therefore, we have negative 0 times delta V. Delta V not 0 because your final V, this is your V final, this is your V initial. So therefore, your delta V not 0, but 0 times anything becomes 0. So therefore, the work done by the system equals to 0. And think about the reverse process. So the reverse process, which means the opposite process, you want to compress this much gas in this cylinder by push the piston, then you can go back to that VI. So in this process, in this opposite process, the work is done on the system, larger than 0. So this process, as it happens in reality, is irreversible. You can make this process become reversible, which means you have to control the expansion of the gas so slow, and then the opposite compression process of the gas also so slow. Do it in such a rate, take forever. So that means you will decrease the pressure or move the expansion of the gas is little by little, so little expansion will take forever, never finish. Therefore, it becomes reversible. All right. So as a conclusion, irreversible cannot be undone by exactly reversing the change of the system, or cannot have the process exactly followed in reverse. And also, any spontaneous process is irreversible. All right. Any questions?
So, Dr. Wayne, whenever work done by the system is zero, it's always going to be irreversible?
Well, that's well, as we said, all the real process is irreversible. Okay, so therefore, no matter the work done by the system zero or not, so definitely, if you see your process in the real life process, the real life process are all irreversible. So then, if you want to make the process reversible, you have to imagine something happen, like what happened in this gas expansion. You want to make that really, really slow. So if you want to have the gas expansion, that means you have to gas expansion or the increase in the volume of the gas is so small, so that happen in a really, really small rate. So that's not really we can do in real life, that because that will take forever. So that has nothing to do with whether the work done by the system equals zero or not. So in this example, we compare work done by system zero and the reverse compression work done on the system not zero. Just give us some example. So give us some example when we have this process happen between the expansion and compression. So they are different. So they are different in that way. That means even though you recover the system into the initial state, the initial volume, temperature, and so on, but something happened to the surrounding is not cannot be restored. The reason in this example, we can see the work done by the system in the expansion process is zero, and reversely is not zero. And we know there's the equation, the first law. So we have delta E equals Q plus W. Okay. So therefore, if W is the difference for the system or for the surrounding in these two processes, then obviously Q will be different. And so therefore, what happened to the surrounding is not exactly the same as before. Even though for the system, you can restore exactly to what you had before.
Okay, thank you.
You're welcome. Any other questions?
Yeah, I'm sorry.
Okay.
So no matter if there's no pressure in the beginning, there won't be any work done at all. But when will there never be pressure?
Say again, I did not get you. If there is no pressure, as we saw from this equation for the gas expansion, so if there is no pressure, that means P is zero, so therefore the work is zero, right?
Okay. Yeah.
But to reverse the process to compress the gas, obviously you have to do some work.
Okay.
Okay. So so even though it seems the energy is restored, the energy and everything is restored for the system because the system get back to the initial state. But something happened, that is the heat for the surrounding is different. So therefore, we did not restore exactly for the surrounding as it did before this process. All right, so so as I said, the reversible process just a hypothetical ideal process. So we can imagine some of those chemical process or those physical process as gas expansion and compression as reversible. So we can do some of those calculations for the enthalpy or entropy, do the calculation for their change, and then we know those quantity, if they are state function, their change only depend on the initial and the final. So therefore, we can use our calculation from the reversible process for the change of entropy or enthalpy to the process that is not reversible or the irreversible process. All right. So in this example, just want you to use your common sense to predicting or identify the process spontaneous node. So some of those you use your daily experience, and some of those you already learned from chapter 5. So you predict whether each process is spontaneous as described, spontaneous in the reverse direction or at equilibrium. The first question is what at 40 degrees Celsius get hotter when a piece of metal heated to 150 degrees Celsius is added. So that's what those kind of situation we did in the experiment in Chem 113. So we take some of those hot metal, remember we take the hot metal out from the oven, then put in the beaker has water, and then we'll see as a result, we did not do anything else, we just drop the hot metal in the cool water. So what happened, the water's temperature increases, and then the metal get cool, the temperature decreases. So finally, the water and metal have the same temperature. So this process, the water get hotter, is spontaneous. Yeah, so we need to think about those processes, whether they are consistent with our experience. Our experience, maybe our daily life experience, or maybe what we learn in some other chapters or other classes. So this water getting hotter when you drop some hot metal in it, that is spontaneous. What we can use is we use the heat always flow from a hot object to a cool object. Yeah, so whenever two objects at different temperature are brought into contact, heat is transferred from the hot object to the cold one. So that is in section 5.1. Therefore, heat is transferred from the hot metal to the cooler water. The final temperature after the metal and water achieve the same temperature, we call that thermal equilibrium, or somewhere between the initial temperature of the metal and water. So this kind of identification is kind of not really exact. So I will give you some of those trivial questions like this one. or maybe some other trivial process like can you predicting spontaneous or not if the broken eggs spontaneously recover into the non-broken eggs. When we see those picture, if we drop eggs, it will spontaneously fall to the ground and break. So the reversible process, the broken eggs to become intact and to become the non-broken eggs in your hand is non-spontaneous. So obviously, as this chapter goes on, we want to study some of those physical quantity we can use to identify our process in a more precise or scientific way, whether the process is spontaneous or not, just using some numbers. So that we can do later on in this chapter. Right. So the second example is predict whether water at room temperature decomposes into H2 gas and O2 gas. Well, so that's we not really learn that those kind of physical quantity yet. So to predict that kind of you will take a chance or ballpark guessing because you know like whether a chemical process spontaneous or not. Obviously, from our daily experience, that cannot happen. So we never see like hydrogen gas and oxygen gas come from water. So that's why so many people or so many scientists or so many companies try to investigate how can make this process happen. So therefore, we can produce H2 gas used in the new way to produce energy instead of using the fossil fuels. Right. So therefore, for the second question B, so water decompose into H2 gas, O2 gas is not spontaneous. So the last question is about those kind of equilibrium. So what happened for this question C is we have a benzene vapor, which is C6H6 gas at a pressure of 1 atm, condensed to liquid benzene at a normal boiling point of benzene, 80.1 degrees Celsius. So don't confuse by if you have the benzene at benzene gas or benzene liquid at its boiling point. So at a boiling point, usually we're thinking the liquid can boil, but if you keep the container closed, so you will have this equilibrium between the gas and the liquid. So this equilibrium is dynamical, which means the liquid will keep boiling, change into gas, then the gas will condense into the liquid. So therefore, this process is equilibrium, and neither direction is spontaneous. So they just equilibrium process. It happens in the same time. So therefore, this process, benzene vapor at pressure of 1 atm and at the normal boiling point 80.1 degrees Celsius, condensed to liquid benzene is non-spontaneous. Right. So we are going to study in more detail about this concept entropy. So entropy, we will use this letter S in this class, can be thought of as a measure of the randomness of a system. So It is a state function. So we learn in chapter 5, what is a state function? Okay, question? Okay, so state function.
Going back, I'm sorry.
Okay.
If we're going back to the previous part where it was how H2 and O2 dissolve back into a liquid. So does changing the state of the matter, does that matter or no? Like if it changes from solid to a liquid, it's reversible, isn't it? So would that still be spontaneous?
Hold on. The reversible process is a hypothetical process. So the equilibrium is the equilibrium. Okay. So even at equilibrium, let's say that you have two processes happen. Don't confuse that by with the reversible. So if you have this, let's say the vaporization and condensation happen in the same time, what happened is in this question C. So you have liquid and gas. They both exist, and this is different. So this dynamical equilibrium is different than the reversible. So which means if you vaporize the liquid, and that's so those process is irreversible. And similarly, if you condense the gas, that's also irreversible. So you can think about two irreversible process just happen at the same rate. Then you have the dynamical equilibrium.
Okay, I understand. Thank you.
Okay, you're welcome. Okay, so the entropy S can be thought of as a measure of the randomness of system. So the randomness of the system, you can think about what is in the system. Your system might have those, let's say, the gas molecules. So the randomness, which means where are those gas molecules? Where are their physical location? And you can also think about how much energy they have. What is the speed they are moving? And what is their state of rotation, vibration? So all those is a measure of the randomness of the system. And so this is a state function. A state function, which means it's change. The change in this case, so this is the change of this state function. It only depends on the final initial state. So therefore, we can use that reversible process as a very good way or good tool to calculate what is our delta S. Okay, so in this example, if you want to calculate what is delta S, for example, it can be found by heat transfer from surroundings at a given temperature using this equation. So you use delta S equals Q REV, means reversible. And then divide by the T in Kelvin. So therefore, we can use those reversible physical quantities to calculate our delta S. Then we can use those results in some other process or in our reality process that is irreversible. So we'll start this equation more in later sections. Okay, so right now we want to see if we have that concept entropy, and we will have this second law of thermodynamics. This second law tells the entropy of the universe increases in any spontaneous process. Remember this word universe? So universe equals these two parts we mentioned. One part is system, the other part is the surrounding. So the entropy change of the universe will equals the entropy change, or the entropy change of the universe will equals the entropy change of the system plus the entropy change of the surrounding. So this results in the following relationship. For the reversible process, delta S universe, which will have these two parts, because universe equals system plus surrounding, so therefore the delta S will equals delta S system plus delta S surrounding. So for the reversible process, that is 0. And this is the equation 19.4 in textbook. In the textbook. I think the other part I will not agree with that. So the other part in the textbook it will write irreversible process larger than 0. So probably I want to say precisely irreversible process will not equal to 0. Then the spontaneous process will be larger than 0. And non-spontaneous process will be less than 0. So anyhow, so this is probably the two equations. All right. So this is the second law of thermodynamics, and then we are going to think about those randomness or entropy on the molecular scale. So we think about in these pictures, two molecules are colored red and blue to keep track of them. And we can see on the left side that picture A has both gas molecules are limited on the left container. So if we open this valve, and the two gas particles can have this 4 possible arrangement. So we call those 4 possible arrangements microstate. So that tells you some idea about the randomness. So this microstate tells us some idea about the randomness of the system. The more microstate, the more random, the more chaos. So this study was initiated by data scientist Boltzmann. So gas molecule expanding or expansion, two molecules start on one side above. What is the likelihood they end up back into that that state A? So we can use statistics. So all together, so they have this B, the fourth state. And you can see for each one of them, for the blue one on the left side, there's 1/4 of the chance. They all together have 4 chance. So it's the blue one on the left along, so it's 1/4. Those are statistics. So the red one along, or the red itself on the left side is also 1 state out of the 4 state. So what is the possibility for either the blue one or red one on the left side, but only one of them? The 1/4 plus 1/4 equals 1/2. So then what is the possibility for both of them on the left side? So statistically will tell you what you do. You will take 1/2 of the chance for each of them on the left side, which is 1/2, and then you also times 1/2 of the chance for each of them on the left side. So that means for both of them simultaneously on the left side, you will have 1/2 times 1/2. So that's why we have this number here, which means both of them ending on the left side. And clearly from this picture, you can see that. Yeah, so statistically, you get that by taking the chance of each of them on the left side is 1/2, and both of them simultaneously on the left side is 1/2 squared. And also from this picture, you can see that. So then, if you increase the number of molecules, let's say you have 1 mole of molecules, so then with the 1 mole of molecule is the Avogadro number. So these 2 become the Avogadro number. So if you only have 2, you probably can think about there's some chance. So when you open the switch, the gas is depending, but still have so 1/4 of chance. So that's 1/4 of the chance, right? So to get this 2 molecule on the left side. But that chance is getting less and less if the number of molecules are getting more and more, which means you will take 1/2 to the power of Avogadro number. So obviously that becomes 0. All right. So therefore, if you increase number of particles here, you might see some other situations, but for here there's only kind of like 2 situations. One is on the left side, one on the right side. So just that means this empty. The other one is evenly distributed. So if you have more, and so then how many of them on the left and how many of them on the right? So you might have, well, let's say you have 4, you might have 3 here, 1 here, or 2 here, 2 here, or 1 here, 3 here. So you have all the possible distributions. So you can use a statistic, so statistical physics or liberal in physical chemistry. You'll get some formula. So then you will have those so-called the formula pretty much just factorization, like those numbers. So you can calculate what is the ratio between those different distributions. And then finally, you will get the ratio, the distribution of evenly, like 2/2 or 1/1. So in this case, you have 1/1 distribution. If you have 4 particles, you have 2/2 distribution. You have 10 particles, you have 5/5 distribution. So the 5/5 distribution will dominate. You will have a formula for each of those distributions, but if you calculate the ratio of the even distribution to the other uneven distribution, you will see that the ratio will become infinitely large when you have this Avogadro number. So therefore, the gas expansion will be evenly distributed between these 2 chambers. So in a large scale, if we have one gas, one ATM, which means we'll have those Avogadro number of gas particles. If you open the switch, so final state will be 0.5, 0.5. If you think about those, where are those gas particles? You might have, let's say you have one more, which means one Avogadro number. So ideally, you will have half of the Avogadro number here and half of Avogadro number here. But obviously, you can also have like 1/4 of Avogadro number, then 3/4 of Avogadro number. But that possibility compared with half and a half will be infinitely small. So therefore, we have this final result, the equal distribution of those gas when we have the gas expansion. Not really you have here as 0.4 and here 0.6. So microscopically, which means when we study how many particles on the left, how many on the right, is still possible. But that number compared with the possibility of that number compared with the possibility of this number will become let's say like very large or become zero if you do the other comparisons. Okay, so therefore, statistically, we can understand gases spontaneously expand to fill the volume. Excuse me. So gas spontaneously expand to fill the volume again. So that is the most probable arrangement, approximately equals molecules on one side or on each side. All right, so that we're still on the so-called statistical thermodynamics. Thermodynamics looks at bulk properties of substances, so the so-called big picture. We have seen what happens on the molecular scale. So on the large picture, we see when the gas is expanding, we have equal pressure on, let's say, on the left side, on the right side, or the even distribution of the molecules. So that's on large side, on the large scale. If you do a molecular simulation or something, obviously at any given instant of time, you don't have that really exactly even distribution, but you take the average on a time scale, you sure that will be evenly distributed. And we have to see what happened on the molecular scale, so that's what we talk about. And then how do we relate it? We will use the statistics, the probability to relating them. And this field is called the statistical thermodynamics. So the pioneer work is that Boltzmann. So that has the concept called the microstate. So when you have the microstate, which means a single possible arrangement of position and kinetic energy or everything else. I think thermodynamics, they don't really think about those electron structures, nuclear structures. So all the possible position of kinetic energy or vibrational energy or rotational energy. So this will give you the microstate. So some people like try to also make the microstate even more complicated. That means including the electron structure. So that's some new interdisciplinary studies. So Boltzmann is the first person who studied those statistical thermodynamics. So he used the microstate. Because there are so many possible microstates, we cannot look at everyone. So you can use some of the formula, calculate how much you have. So we'll use W to representing the number of microstates. And so entropy will be a measure of how many microstates are associated with a particular macrostate. Like macrostate, you know that before. For example, if you have 1 mole of H2 gas at a temperature 25 degrees Celsius, at pressure 1 atm, and then have some volume. So this is a macrostate. So in this macrostate, we know how much we have, what is the temperature, what is the pressure, what is the volume, and how many possible those microstates, which means in that volume, where are those H2? How fast they are moving? Are they vibrate? Are they rotate? What's the way they are vibrate? What's the way they are rotate? So those each one possible combination will give you one microstate. The connection between the number of microstates and entropy of the system is given by the Boltzmann equation. So S is entropy, K is the Boltzmann constant, W is the number of microstates. So yeah, as what we said here, you don't have a chance because so many possible microstates, and you don't have time to look at every possible those state, but you can use some calculation to see what is the number. And then you put it into this equation, it's kind of a very simple equation, but it's tedious and difficult sometimes to calculate this W. And once you have the W, you put into this equation, so this Ln is the natural log, and then you use this K, you can get the S. Okay, so in the textbook, there's some of those examples to calculating gas expansion to see what is the delta S. But if you don't have the time to do those calculations, you can just get some of those comparison. Let's say since entropy is a state function, the final value minus the initial value will give the overall change. So in this case, as increase in the number of microstates, so if you have the final microstate, so W final larger than W initial, that will result in a positive entropy change mode disorder because you can simply use the Boltzmann equation. So delta S will equals K ln W final minus K ln W initial, and use mathematical rule, so that equals K times ln W final W initial. So either way will tell us this delta S positive or negative depend on the number of W final and W initial. So if, for example, W final is larger than W initial, which means we have more chaos, and then you have this ratio here larger than 0, then Ln larger than 0 is a positive number, K is a positive number, so therefore delta S is a positive number. Oppositely, so if this is small, this is larger, so you have a number smaller than 1, then Ln for a number smaller than 1 is negative, so negative times positive negative. That means our delta S will be negative. So this is kind of very useful way we are going to use our Boltzmann equation in this class. We can think about when can we have a delta S positive, when can we have a delta S negative. So the conclusion is when you have more disorder or more number of microstates, then your delta S is positive or larger than 0. Right, so all these common variables like volume, temperature, state change, so they will have some effect on the system, on the entropy. So for example, if we increase volume, and there will be more position possible for the molecules. So you imagine a small volume and a larger volume. So therefore, in a larger volume, so you will have more location for those molecular or particles in the system, therefore become more chaos, therefore will increase the entropy. And how come the temperature will also influence our entropy? So we can think about what we saw, this Boltzmann distribution of the speed of molecules. So if we increase the temperature, the average kinetic energy increases. So this results in a greater distribution of molecular speed, recall from table 5. So therefore, there are more possible kinetic energy values, resulting in more microstate. So therefore, increasing the entropy. So this picture in this at the bottom of the screen tells us we have a system. Let's see, at 80 Kelvin, we have this distribution of the speed. So we kind of have a narrow distribution. So most of them have a speed about 200 meters per second. Okay? And if you increase temperature, let's say to 300 Kelvin, and then you can see this green curve and the distribution become broader, which means there are some molecules at 200 and 300 and so on. So therefore, you have quite a different number of this speed. So obviously, when the speed are different, the kinetic energy will be different. So therefore, you can have more different microstate. And as we said, the microstate number increases, your entropy will also increases. So in this one, we even did not considering the effect of the volume yet. Just think about if the temperature increases, so therefore we have a broader distribution of the speed of those gas particles. Therefore, there's more microstate. Okay, any questions? Okay, so in addition to the kinetic energy, those molecules can also have some other motions. Yeah, molecular usually exhibit several type of motions. The translational motion that give us like the kinetic energy, which is the movement of the entire molecule from one place to another place. So vibrational motion is the periodic motion of atom within a molecule. So these three pictures at the bottom tell us three possible way of vibration for this, let's say this water molecule. So we can have those stretching between the oxygen atom and this hydrogen atom. We can also have the squeeze angle between the hydrogen atom, or we can have the stretching of the H atom, oxygen atom in a non-symmetrical way. So one stretching, the other one compressing. So those are all possible vibrational motion for the molecules. Rotational motion is the rotation of the molecule about axis. So we can imagine there's one axis, for example, goes through this oxygen atom and goes between these two hydrogen atoms. Then your molecule, then your water molecule H2 can rotate or spinning on this axis. So this is rotational motion. So obviously that will depend on the temperature and then how many of those molecular or atom we have in the molecule also will increase you have more atoms in the molecular, and then also the increased microstate. So here we have 3 atoms in water. If you have those complex molecular, like in the DNA or protein, that will definitely dramatically increase those vibration, rotation, and so on. All right, so the number of microstate and therefore the entropy tend to increase with increase in temperature. And we saw the reason when the temperature increases, our distribution of the speed of the molecular increases. So therefore, we have a variety, a larger variety of the speed of the molecular. If the speed are different, the kinetic energy are different. So therefore, we have a more microstate. When the volume change, and obviously you will have more position or more location for those gas molecular or gas atoms. So therefore, you have a larger number of microstate. So the number of independently moving molecular, which means if you have a temperature the same, volume the same, if you just increase how many molecular you have or how many atoms you have, and then as the number of molecular or atom increases, the number of microstate also increases. Okay, so you can also see this relation between entropy and physical state. So entropy increases with the freedom of motion of moleculars. So typically we'll have this 3 states, like a solid, liquid, and gas. So for the given amount of the material, let's say we have a 1 gram of water, and then you compare this 1 gram of water for the same amount of sample, maybe 1 gram, maybe 1 more, and you have this comparison. So this entropy in the gas state is larger than the entropy in the liquid state, which is larger than the entropy in the solid state. So entropy of the system increases for processes where this following is true. So if gas from either solid or liquid, so the entropy of the system increases because we have this comparison here. And again, you have to see compare the same amount of sample. So liquid or solution from solid, which means when solid dissolve into liquid or get into solutions, so the entropy also increases. And the number of gas molecules increases during chemical reactions. So these are some of those you can use to predicting the increases or decreases of the S or the entropy without using some numbers. And we have some number available for some of the common elements or compound in the table, appendix C in the textbook. So sometimes you can use the number, sometimes you can use this few rule here on this slide, on the previous slide, and to decide whether your delta S or the S increases or decreases. So this slide shows us, first we want to see the state change. So state change for a fixed amount of H2O. And you can see going from ice to liquid water to water vapor. So increasing entropy, even though in the last picture, we only see a few H2O molecular, but that's not really what we want to compare. We want to compare the same amount. So as we saw from last slide, and if you produce liquid or solution from a solid, and the entropy also increases, because you can imagine if you take some of those ions away from the solid here at the bottom, and then you take them into the solution. Let's say this is the aqueous solution, water is a solvent. Then you can see those ions can have more locations, more places to go, so therefore become more chaos. If you do the opposite, if you make a solution from gas particles, that will be opposite, because gas become floating in many places. Then you put them in a solution, then become liquid, so therefore your entropy sure decreases. So pay attention to the word you make the solution from solid, and that will increase the entropy. So on the last slide, we also talk about the chemical reactions. So in some chemical reaction, you might starting with some of those gas and also ending with some gas. So you will just, because the gas will dominate, the gas has a larger entropy. So therefore, to predicting the sign of delta S for a chemical reaction, you pretty much can concentrate on those gas reactant or gas product. Okay, so in this example, let's say we have not really what we say here. So we have if we have this other reactant, we have coefficient 1 here, coefficient 2 here. So we have 3 gas reactant, then we have 2 gas reactant. So in this process, so this delta S is less than 0, which means your entropy decreases. But in general, you will see the number of gas molecule increases during chemical reaction, then you will have those entropy increases. But this just a general rule, and this here is not really applied to this chemical reaction, because in this chemical reaction, the gas molecules decreases. So just in case, if you have chemical reaction, the gas molecule increases, then you will have your entropy S increases, or your delta S larger than 0. For this one, for this chemical reaction, so our delta S is smaller than 0. All right, I think we can finish this example, then we will finish this lecture. So you want to predict whether the delta S is positive or negative for each process, assuming each occurs at a constant temperature. So the first one you can say is a state change. So we change for all those, assuming we keep the same amount of material. So we change from liquid water to gas water. So what do you think? In this first process, when we have H2 liquids changing to H2O gas, what will be the sign for delta S?
Positive?
Yeah, so you get that right. Is that Jared? Jared? Okay. Okay, so this is positive. Why is it positive?
It's because it's going from a liquid to a gas, so the motion of the molecules is higher.
Yeah, I think that's Jose.
Yeah, it's Jose.
Okay. Yeah, Jose, you got it right. So because we change from liquid to gas, and in gas we have more position, more location for the gas, for the water molecules. Therefore, we have entropy S increases. Therefore, delta S other than 0. Very good. Very good. So what about the second reaction? The second reaction, we can see we have Ag plus ion in aqueous, chloride ion in aqueous, then become solid. So you kind of go from liquid to solid, then your delta S should be, your entropy should decreases. So therefore, delta S should be less than 0. Right. So then question C. So let's see, what will be the sign for delta S? We see our reactant. One reactant is solid, then we have 3 gas. That will produce two solids. Okay, any answer? Okay, go ahead.
Is it negative?
Is this negative? Yeah, this is negative. Who is this?
Madison.
Medicine. All right, so that's also negative. So why medicine? Why is this also negative? I think the reason for you know because we starting with some gas, then we finish with our solid, so therefore our entropy decreases because in gas we have more chaos or a larger S or larger entropy. Very good. So then this last question, delta S. So pretty much this chemical reaction, you have one N2, one O2, that have two NO. So what will happen to the delta S?
Is it 0?
Yeah, very close to 0. Is it still medicine?
No, this is Ola.
Zola?
Ola.
Ola. Okay, thank you, Ola. Yeah. So this close or closer to 0. So approximately 0. All right. So today's lecture, we have a lot of those concepts, and we studied those entropy, and we studied the second law of thermodynamics. So we can use this sign for the delta S to predicting the reaction spontaneous or not. So well, here just the sign for the chemical reaction. But the thermodynamic, the second law tell you the delta S universe larger than 0 is spontaneous. So here we just, those are just delta S system. So here the delta S system. So then we come back like next week, and we will studying more of those thermodynamics, and we hope we will get some a good pseudo quantity and use it to predicting our spontaneity of the chemical process. Okay, any comment or questions?
Dr. Wang, if we have questions in regards to the lab, can we ask you here, or do you want us to move to your office hours Zoom?
We can continue, Stephanie, right?
Yeah.
Okay, yeah, we can continue. And what's the question? Yeah, feel free to stay or to go. Yeah, if you have a question, just we'll keep. Yeah, what's the question for the lab?
I'm just having trouble finding equivalence points for the graphs.
Okay, so usually you will see. Yeah, so for the lab, I see. I wonder if you're still here. Just use first. You want to follow the lab manual and read the manual step by step. Then use those file or use those computer simulation to gather in data. Okay, so for the equivalent point, if you let's say if I go away from the screen, and I will show you how you get some of those graph, and from the graph or from the data, you can predicting the equivalent point. Do you, Stephanie, do you have any like a particular question about the equivalent point?
No, it's just I just need one. Yeah, just one example, and I'll be fine.
Okay, so let's see one example for the equivalent point. Let's see the titration. Okay, so let's see titrate. Let's you titrate the weak acid with a strong base, the acetic acid with NaOH. So what you did is you have those numbers, and see after you enter those volume for the NaOH, you get those pH, and So then you take this volume and pH, you have this graph. So one way to identify your equivalent volume or equivalent point is make a graph like this. Okay, so I take the first two columns and then I go to insert. So I have this pH with volume graph. Okay, so one way you can identify your equivalent, you can see the jumping here. You see the quick increases of the pH in this area. Okay, so you can point your cursor to one point in the middle. Then you can see the number here, and then you see the number here. So on the screen is 10 and 8.882. So therefore, the 10, it will be the equivalent volume. Get that?
Dr. Yeah.
Mhm.
Thank you so much.
You're welcome. Yeah.
When there isn't like a exact point in the middle, do we just estimate?
Yeah. Is this Zania?
Yeah.
Okay. So let me show you. That's a good question. So let me show you one example. You don't have exactly, so you titrate the salt, right? So let's say I
Yeah.
titrate the salt unknown number 1. And we use HCl. And you will see the graph. Okay, just a minute. So the graph looks like that, right? So obviously you see the pH change not that sharp. It's kind of going from starting from this point here and go to this point here. So yeah, that's why you will just take some point between there. You might, if you choose this point, if I choose this point, I move my cursor on this. Well, I hope that, okay, so I have to click on this frame. I move my cursor here, it will show me the number, yeah. So show me the number like 3.5. So you can either use this 3.5, or if you prefer, probably some number even after 3.5. So if you do that, you see somewhere between 3.5 or 4.0.
Okay.
Or yeah, if you argue probably before 3.5, because this looks like a very sharp drop from 3. So this is 3, and this is 3.5. You see where I got the 3.5?
Yeah.
Okay, good. So yeah, just do your like own like adjustment, and you just give me any reasonable number. Yeah, so that's how you get the equivalent point.
Okay. Thank
Yeah.
you.
You're welcome.
Dr. Wang,
Yeah.
I have a question.
Mhm.
So the equivalence point is when the graph, like the
This is Daya, right?
yeah.
Okay.
Then yeah. It's when it start raising or just like the middle.
Yeah. I think just the middle. Just identify the very rapid decreases or increases region. Then try to locate the middle. So this just visually. If you want, you can go to YouTube and to see how you get the first derivative from the titration curve. So if you have those data here, you have the volume kind of the x-axis, you have the pH the y-axis, you can calculate the first derivative. Okay? And also those number, you can change. I think those Excel files kind of resilient. You can change them into different numbers. I think that their menu tell you to use those numbers. You probably can fine tuning those volume near the equivalent point to put more point here, and then you can probably identify the equivalent point a little more accurate.
So for example, in that table, which one is the equivalence point?
Yeah, that's why I said probably if I want to make the work simpler, I will just using this middle one. I just use
Okay, like
3.5. Yeah.
pH of 3. 3.5.
Yeah. So the volume is 3.5. The pH is 2.903.
Okay, perfect. Thank you.
You're welcome.
Is that it for today?
Yeah. So today the lecture just this. So the lab, I think I will keep using the same format. For next week lab, I also find a simulator, which about those voltaic cells. So we can choose different cell, different metal. We can use silver, we can use copper, we can use lead. We can also use different concentrations to make a battery. So then the second part of this week's lab, next week's lab will be you want to measure the battery. Probably I also want to make those Excel file, and then just click on those batteries, then you measure the voltage for the battery, then you find out what is that battery and for how many cells in the battery. Yeah, so we will try to keep using try to do those activities in the lab manual. If we do the lab in person, so I think those activities in our lab manual are very good. So I try to still using those activities, but we don't have in-person labs. Therefore, I either using the online or offline simulators, and then some of those part of the lab, I will just give you the Excel file, you use it to get the data.
Dr. Wang?
Thank you, Dr. Wang.
Welcome. Okay.
Dr. Wang, the lab report for the pH, the titration with sodium hydroxide, when you ask for the acid dissociation constant Ka, do you mean like the Ka equilibrium or like?
No. You mean that question is for the acetic acid, right?
Yeah, acetic acid and the sodium hydroxide.
Yeah. So what you do if I go back to that titration, and you see there's so when we study that chapter, I think that will be chapter 17, and you see the equivalent point for this titration. So we have this acetic acid and NaOH. So we have this titration of acetic acid with NaOH. We have the pH. Then, as what we said before, we can identify our equivalent point. So you move your cursor here, you see the equivalent point is 10. 10, yeah. So then the pKa, so you first identify the pKa by go to the half equivalent. So if 10 the equivalent and half will be 5. So you go to 5, I think it will be this point. Okay. So once you get this point, you see it's 5, then 4.785. So 4.785 is our pH, our pKa, sorry. So therefore, once you get the pKa is 4.785, you get a pKa. If you want to get a pKa, you're going to get a Ka. So you just take a 10 to the negative 4.785. So what you do, you can use your calculator. Let's see if I can do that here. Yeah. So 10.
We just use the pH for the half equivalent point and use that.
Yeah, you get it. So you use a pH at half equivalent point as pKa. So pH at half equivalent point is pKa. See what I type?
Thank you.
Welcome.
Dr. Wang, for the lab, do you only want one person to turn it in, or does everyone turn it in individually?
So if you do the group work, just one person turn in, and then in your lab report, you probably want to just tell me this is the group lab report and group member name.
Okay, and then since you said to attach pre-labs with the lab report, do you want everyone in the group's pre-labs attached to it, or just?
Yeah, it'll be easier for me. Just if you can just attach, you just if like this week you write the lab report for the group, and then just ask your group member to give you like all your pre-labs, and then you can use some of those technique and just put all the pre-lab into one file, and ideally you save them as a PDF, and then you just upload to the website.
Okay, thank you.
You're welcome.
Dr. Wayne, about that pre-lab. So I turned in the lab
Okay.
report for my group with my pre-lab, and then everybody else turned in their pre-lab separately. But is that okay for now? And then next week we'll do it the way you just said to do it?
Okay, yeah, nice, yeah.
Okay, thank you.
You're welcome.
Have a great day, bye.
Okay, you too, bye.
Have a good day, Dr. Wang.
Okay, yeah, bye.
Bye.
Bye.